Okay, so last time we were working on this two-band model in which we had one orbital, a p orbital and an s orbital, the two atoms in the unit cell. And we worked through that, and we get this kind of band out of that, a direct gap, one conduction, one valence band that are identical. Then we showed how the that off-diagonal matrix element T is related to the effective mass and your lattice constant. So, for the type of material that you would be using a model like this for, you know what the effective mass is. So, knowing the mass, you know the band gap, you know the lattice constant. That's how you would choose your T. And then we showed for the three band models that we've considered so far, the parabolic effective mass in red, the one-band tight binding in green, and this two-band tight binding in blue. This is how they look and how they were differ and how they are the same is that they all have the same effective mass at k equals 0 at the band conduction band edge minimum. And the other thing is that they do differ in that this, if we define this band width that we talked about earlier, the band width of your one band tight binding model is greater than the band width, this bottom to top distance and energy of your two band tight binding. So the two band tight binding model is more non-parabolic. So we use this not only to get two bands and treat problems like interband tunneling and tunneling that we'll talk about today, but also just to get more non-parabolicity and get a better estimate for the resulting density of states, which is what we talked about last time. And so often in textbooks that you'll see when they're treating things like scattering rates, where you have to integrate over a final density of states, often they want some correction to parabolic just to get a better number. And so they don't use this full EK relationship. They just use the density of states that you get when Ka is basically small, and you can do a first order expansion of this sine term to get this, and you work that EK relationship out, and finally you get something that looks like this. If you just work that through, the only approximation so far is replacing the sine squared Ka with this, right? That was the approximation that we made, and then everything else beyond after that we just worked it out. And you get to this, where you have, for your parabolic model, you just have E equals h bar squared k squared over 2m star. And now you have this extra term, what you people call this correction term. And the correction is proportional. The magnitude of that correction is proportional to 1 over the band gap. So for large band gap systems, that's not very important. For small band gap systems, it's more important. And then we said that in your textbooks, what you're really going to see is an expression that looks like this, where that 1 over the band gap is just replaced by a parameter alpha, which is really a fitting parameter that gives some best fit to the known density of states. And you can find values for alpha in various journal articles and books. And then we went on to calculate using this EK relationship in the red box, we went on to calculate what is the density of states using this really fundamental definition given here, which you've probably never seen before. And Alex, I think is Alex Blandon just starting to do density of states? Has he done that yet in 202? So he probably doesn't, introduce it like this. But if you think about this expression just sort of from an intuitive point of view, all you're doing is you're summing this K as a sum over the whole Brillouin zone, and so you get a contribution whenever your energy is equal to the E of K you get from your dispersion relationship. When that's true, then you get a contribution. When it's not, you get zero. So you're just summing all the contributions, or in the Brillouin zone, of when your dispersion is equal to the energy of interest. And so those would be all the states at that energy. That's really what you're seeing here. You're just summing over all the states at that energy. And to actually evaluate it, you have to turn it into an integral, which we talked about before. And so we went ahead and did that and got this. If it's not a function of angle, you can get it down to an analytical expression that we finally, after reviewing some properties of the delta function, we finally got it down to this analytical form for a three-dimensional density of states. And then we went so all then we needed was the derivative of the dispersion that goes in the denominator, and we have to write K as a function of energy that goes in the numerator. So here is our K as a function of energy. Here is our derivative that goes in the denominator, and we just plug those in to get the final form for the density of states here. And then we showed how these, it initially will start off looking like your parabolic one, like this, but then as the energy increases and becomes comparable to 1 over alpha, it starts diverging and eventually becomes quadratic in energy. And this becomes important when you're then trying to find where the Fermi level is for fixed doping. And I mentioned that even though we derived it for, it gives you a direct gap semiconductor, people use it for silicon, which is indirect, and the conduction band is actually way over here near the edge of the Brillouin zone. And it's just then alpha just becomes a fitting parameter, something that gives you a best fit that they use for silicon. And finally, what we started talking about at the end was using this model for tunneling and seeing how it affects the answer to the tunneling problem. And that's where we're going to continue now. And so the example is this system of indium arsenide, aluminum antimonide that people grow by MBE. And we want to understand the tunneling. So these are our band edges, our conduction band edges of the indium arsenide and aluminum antimonide. And we want to understand, if we send an electron in here, how it's going to tunnel through the aluminum antimonide. And in the WKB approximation, this transmission coefficient is just roughly e to the negative 2 kappa d, where kappa in the effective mass in your parabolic model would just be given by this. And it's sort of just turning your dispersion upside down, measuring from the top of the barrier, how deep you are from the top of the barrier in terms of the energy argument that goes here under the square root. And I guess I know you did this in 201 since I taught it once, but I don't know exactly what Alex covers, Korotkov. So let me just see if I can quickly derive that, and then we'll move on. So in the barrier region, my wave function is going to be some exponential. I don't know why I switched to z. Anyway, so z would be the direction going through the barrier. And I'm coming. If you're above the conduction band, if you're a plane wave, then psi is just e to the I k z. So it's just like to go from one to the other, I just let K go to I kappa, and my e to the ikz becomes e to the negative kappa z. And so the way you see that starting from Schrodinger's equation, let's see if I do this without making a mistake. So this would be the potential at the top of the barrier. So I'm just imagining I have a uniform system with some potential VB. And usually you have the energy on the right-hand side, but I'm going to move it onto the left-hand side of the equation. Right? That's Schrodinger's equation. Usually you have E psi on the right-hand side, right? That's Schrodinger's equation. And if we just put in the solution into this psi equals E to the negative kappa z, plug it in, take the second derivative, see what you get. You basically get that h bar squared kappa squared over 2 m star is equal to VB minus E. Right, just plugging that solution for psi into the equation above it. And so that becomes your sort of eigenvalue equation relating energy to kappa, and you get exactly what I wrote down on the previous slide, that when you're below the top of the barrier, then this is the form of your wave function, and kappa is just what I wrote down before, square root of 2m star, where E is less than some energy below VB. Okay, that's simple how that happens. Let's just take the conduction. If we take the conduction band edge at E equals 0, then we have above 0, or above the conduction band edge, we have E equals h bar squared k squared over 2m star. And below, you're just going to have E is, to go from one to the other, I just replace k by I kappa. So h bar squared over 2m star times I kappa squared, which is your minus h bar squared kappa squared over 2m star, or kappa squared, sorry. So the only point is to just go through and show you that it is indeed correct when you're below the top, when you're below the barrier in the band gap, to just replace k by I kappa, at least in this simple parabolic model. And so sometimes people plot this like this. So this would be my k axis, this would be my kappa axis. People who worry about tunneling, this is your usual energy coordinate. 0 is my band edge, and so above the band edge I just have my usual, and this would be in a parabolic model. And now these parabolas are identical. Below the band edge I have this relationship here. So basically for tunneling, you just flip the normal EK plot upside down, and so you're going to be tunneling through a barrier at some energy, and you go over here, you find your kappa, and that's what determines your tunneling. Your tunneling is e to the negative 2 kappa d, right? It's this kappa that determines how well you're going to tunnel through the barrier. It's not the energy, it's the kappa. And so it's important that you know what energy you're at, you know where you are with respect to the band edge, but it's the band model that relates the energy to the kappa. And so you need a good band model to get the right kappa, because if you notice, this is exponentially dependent on kappa. So if kappa is off, then you'll be exponentially off in your tunnel current. So let's look at what that means for this two-band model. So for tunneling, we're going to take our EK relation that we derived, and we're going to replace K by I kappa. And since K just shows up in the sine function, you make use of the identity that sine of I theta is equal to I sinh theta. And that's what we're going to do. So that sine squared is going to become a sinh squared in our dispersion relationship. So below the top of the barrier, you now have E is equal to Eg over 2 plus or minus square root. So this is in the band gap. Right? In the band gap of our 2D material, of our two-band model, quantity Eg over 2 squared. Right? So that's in the band gap. That's what the energy kappa relationship is in our two-band model. And so if you plot that, right, there's still these two branches. And at some point in the middle, they're going to intersect. And so let me just draw it. It'll be easier to see. So I'm going to draw it like what I did before with the propagating states on one side and these evanescent in the barrier kappas on the other side. So this is our valence band edge at 0, the way we set up this dispersion. And this will be our conduction band edge at EC, which is the band gap, the way we set up that dispersion. And so above, in the valence band, you have your normal dispersion. I'll draw some edge to our Brillouin zone. And so this is at what we've drawn before. The dispersion you get that we've already drawn from our two-band model, right? Those are the propagating states above the conduction band edge and below the valence band edge. And now in the band gap, this is what you're going to have. So it wraps. This thing wraps smoothly between the conduction and valence band edge. So if you go back and you were to plot this function, you would see it would wrap smoothly around. When kappa is 0, it's just, the two band edges, and then, you just have to go through it and plot it. But this is what you get from this model, and this is what you're going to, in reality, even with more sophisticated band models, get for any direct gap material. This what they call evanescent band will wrap around and connect the conduction band to the valence band. And the effective mass model, which is parabolic, well, they all start off the same, but this is just parabolic, so it's going to keep going out and down forever. This would be the effective mass model, and the other is your two-band model. And so as you move away from the band edges, these two, the green line and the red line diverge. And so if I'm tunneling at some point in the band gap, so I'm tunneling at some energy, right? I know my energy. I come over here, I need to find my kappa. The two-band model gives me this kappa. The effective mass model gives me another kappa. And since the tunneling rate is exponentially dependent on the kappa, I can go badly wrong. If, for example, I'm down here, and this is exactly what happens in this indium arsenide aluminum antimonide problem, which I'll show in a second. I guess the other thing is that right at the they're at the midpoint when Eg over 2, I don't know if this is particularly enlightening, is 2t sinh kappa A over 2. So that's when you're halfway between, well, you're right at halfway in the band gap. And this point, for people who do tunneling problems, is that's sort of when they consider that you've moved. If you're on the lower side of that, you're kind of in a valence band state. If you're on the upper side, you're in a conduction band state. They call that a stationary point in the tunneling problem. So if we look at what this means for the tunneling problem I originally drew, where we have our indium arsenide, now I'll draw both the conduction and valence band, our aluminum antimonide, and our indium arsenide. This is what the bands look like for this system. And so this wrapping that I drew in red on the EK plot, if I superimpose it on this band diagram, it wraps around like this. And so even though I'm an electron coming in here and tunneling through the barrier near the conduction band edge, I'm actually below the midpoint of this wrapping. So I'm actually tunneling through, as far as the aluminum antimonide is concerned, I'm tunneling through the valence band, is the way to look at it. I'm below the midpoint here, I'm about down here. So I'm really tunneling through a barrier presented by the valence band. I'm tunneling, through a point down here. And so if you think in terms of the conduction band and use your effective mass model, it will be utterly, completely wrong. Your kappas will be completely different because this is already wrapped around. It's already coming back to the valence band. Your parabolic model has just gone way out like this, and you'll get it totally wrong. So this is one of these systems where you have to go beyond your simple effective mass model to deal correctly with the tunneling. And in general, as you move away from the band edges, again, you can think of this as a correction to the parabolic model, right? This is parabolic, and this is some correction. Initially, in some energy close to the band edge, parabolic is always fine. As you move further away from the band edge, either in the tunneling problem or in the propagation problem, that parabolic model is going to break down on you. So this is where you need a better band model to deal with that. Okay, that brings us to the end of this first section of simple band models. The next thing is we're going to be doing is start to derive the band structure of silicon. So I have this review of everything we covered so far, but I think maybe instead of this review, you'll find in those PDF notes, it's sort of a 3-page summary of everything we've covered so far. So if you want a concise summary of where we've been, I'd say look at the PDF notes that are up on iLearn in the course materials.
What page exactly is it?
Well, the page numbers are they're called here 3-1 through 3-3. So about this far into it. So I think, I think there's just one big PDF file and one of the first items under course materials. And 3-1 just gives a summary, 3-page summary of everything we've done so far. So, I can just, we've talked about the parabolic model, then we talked about solving the parabolic model using the finite difference approach, where we discretize it, and we showed that gives exactly the same result as your single band tight binding model. They give you this identical cosine band dispersion, either doing finite difference of the effective mass or single band tight binding. And people back in the 80s used to actually argue and say, I'm doing single band tight, I'm doing a tight binding model, and therefore it's more accurate than finite difference. Actually, that's all the same thing. And then we went on to do the 2-band tight binding, where we put one pz orbital on the anion, one s orbital on the cation. form your block sum, one block sum for each orbital, and so your basis in K space for each K is two orbitals. And you can solve each K all by itself, giving you a 2 by 2 Hamiltonian that's K dependent, and we calculating the eigenvalues of that, we get our E versus K relationship. So that's what we've done so far, and now it's time to start going beyond into a real crystal. Okay, so what I'm going to start with is you can find in one of the references on iLearn, it's a chapter from the book Fundamentals of Semiconductors by Ewan Cardona. It's a classic book. There aren't many chapters that will make sense to you, but this follows closely a few sections of chapter 2, and those have been uploaded. You can find them, copies, on iLearn. Okay, so in particular, we're looking at section 2-7, which is a tight binding, or LCAO. This is your linear combination of atomic orbital approach to band structure. And in particular, we're going to be looking at what they call the tetrahedrally bonded semiconductors, which are the ones that we've been mentioning all along, like silicon, germanium, gallium arsenide. Silicon, germanium, gas, but not, for example, gallium nitride, which has a different crystal structure. And if you look at the periodic table for all of these elements, the valence electrons are in the s and p shells. So we're going to be dealing with s and p orbitals and their overlaps. And so these orbitals, these s and p orbitals, they're going to form your molecular bonds. So we'll start by drawing some pictures and talk about 3 different type of bonds. S sigma, P sigma, and P pi type bonds. So the first one are the S states. If you take 2 S states, one on atom A, one on atom B, they can form either a symmetric or anti-symmetric combination, and they will give you, as we've already discussed, a bonding type orbital. If I add them together, the electron cloud sort of encompasses both atoms, and if I subtract one from the other, I'm going to get an anti-symmetric wave function. So one will be plus, one will be minus. These are both sigma bonds. One is the bonding, and one's anti-bonding. So sigma bonding and sigma anti-bonding. The bonding is always the lower energy state. Anti-bonding is the upper energy state. And that's about all there is to say about s orbitals, because they're spherically symmetric. That's about all, the only way you can combine them. If we have 2 p states, there's a little more that can be done. There's going to be two configurations, 2 types of bonds. And so the first one is the sigma bond. This is where you have the p orbitals lined up end to end like this. This is kind of funny because they have this, plus and minus sign. Actually, you have the bonding orbital is made if you subtract one from the other. And if I subtract the B1 from the A1, then I end up with a wave function cloud that encompasses the whole space in between the A atom and the B atom, plus, minus, minus, right? So if I subtract B from A, that's what I'm going to get. If I subtract B from A, right, I'm going to get something that looks like that. And if I add them together, so this would be the bonding one and the lower energy. And if I subtract them, that's when I get the anti-bonding. So when I add them together, the 2 central regions kind of cancel each other, null each other out in between the 2 atoms because they're opposite signs. And so this would be your anti-bonding, your higher energy state. And then again, if you look at the signs, again, the lower energy state is symmetric around its center, right? If I just invert it, flip it around its center, nothing changes. Whereas the upper one is anti-symmetric around its center. If I flip it around its center, the sign of the wave overall, what you call molecular orbital changes. So the molecular orbital is that entire thing. Right? If I flip the upper one around the center, its sign would change. And this is always true. The excited state will be anti-symmetric, and the ground state will be symmetric. And these are, so as I said, these are sigma bonds from p orbitals. Guys are anti-bonding. And we'll talk about pi bonds in a minute, but you run into these kind of bonds a lot in molecular molecules. And this would constitute, say, the LUMO, or it could constitute the LUMO, the lowest unoccupied molecular orbital. And then this would be the HOMO, which is the highest occupied molecular orbital. Usually, if there's pi bonds around, that would be formed, the pi bonds will serve that, which we'll talk about in a minute. These kind of bonds will also form in any carbon, like carbon nanotubes, graphene. They're not the ones that we usually worry about for electronics because they're pretty far away from the Fermi energy, and we'll talk about that in a second also. But let me first introduce the third type of bond, which is a pi bond. So number 2, and for electronic structure, these are the most important because they tend to be closer to the Fermi. The bands that form from these tend to be closer to the Fermi energy. And so now, if I have 2 atoms, my A and B atom, and my p orbitals are aligned like this, again, I can either add or subtract them. And if I add them together, I get my bonding state. And since they both have a null right at the atom, there's always that null will always exist, but the wave function will extend across the 2 atoms with a null right in the plane where the atoms are. That's never going to go away. And if I subtract them, then they kind of kill each other off in the in-between region. And I'll flip the sign of the B atom if I'm subtracting the B atom from the A atom. So I'll end up with something like this. So this would be my pi anti-bonding and pi bonding. And again, this is around the central point between the A and the B atom. This is the ground state, it's symmetric. And the upper one is anti-symmetric. If I flip it around the point in between the 2 atoms, I flip the sign of the overall wave function. Right, because one is plus minus, the other is minus plus. It's anti-bonding and anti-symmetric up here around the central point between the 2 atoms. And so, if you think of a carbon atom, it's going to have 3 p orbitals, px. Well, in a minute, talk about what we mean by px, py, pz, but you can choose your basis so that you have 1 p orbital oriented along each Cartesian coordinate. So one aligned along x, one aligned along y, and one aligned along z. And so, like in the homework problem you're doing right now, if you've looked at it, you've got this chain of carbon atoms, and we can choose our basis. So we would have p orbitals like this, and then you would have, let's call this say x, and then you would have py sticking out in this direction, and then you would have pz coming out of the page. So I drew px and py, you'd also have a pz coming out of the page. That would be, if you just look at the p states, your basis. It's a little tricky. Okay, if we look at the matrix element due to these guys that are pointing towards each other, they're going to have the most overlap. They're going to have much more overlap than the 2 red orbitals, right? Because they're pointing directly towards each other. So that matrix element, the T, this forms a sigma bond. I'll call it T sigma. Is going to be significantly greater than the matrix element that comes from the two red orbitals. I'll call that T pi, since that would be a pi bond. Right? The two red orbitals would give you a pi bond. The two blue orbitals would give you a sigma bond, and that sigma bond is much greater than the pi bond. Right? Furthermore, if you think about integrals and symmetry, there is no matrix element between the red orbital and the blue orbital. There is no matrix element between the red orbital and the blue orbital, because if you take a line of symmetry here right through the center of the atoms, the blue orbital with respect to y, call this the y direction, the blue orbitals are symmetric with respect to y. If I rotate them around y, nothing happens to the blue orbitals. The red orbitals are anti-symmetric with respect to y. So if I do that integral, I'm going to get 0, just because they have opposite symmetries. One's symmetric, one's anti-symmetric with respect to y. Or another way, if you think of a matrix element between a red orbital and a blue orbital, because of the sign change of the red orbital, half will be net positive, half will be negative, and they're going to cancel out. Okay, so these orbitals decouple, and they only couple to each other, and we know how to solve 2 by 2 Hamiltonians. So the sigma I'm going to have, and if I just set the carbon energy to 0, I have 0 T sigma, 0 for the sigma bonds, and 0 T pi, 0 for the pi bonds. And so the energy for the sigma bonds are just going to be plus or minus T sigma, and the energy for the pi bonds are going to equal plus or minus T pi. And the 0 in this case is where the Fermi energy is. And so pictorially you end up with the two energy levels, T pi minus T pi, and the energy levels for the sigma, T sigma, and minus T sigma. And your Fermi level is right in the middle of all that. And so for electronics, all you care about are the states near the Fermi level. And since these the sigma bonds are significantly larger than the pi bonds, they're a full electron volt or more away. They just don't matter for the electronic part of the problem. So that's sort of an intuitive picture of sigma bonds and pi bonds that you run into all the time doing called quantum chemistry, calculating electronic structure of molecules, and also graphene and carbon nanotubes. And when you do your the graphene homework problem, you're only going to be worrying about the pi bonds, because those are the ones closest to the Fermi level that matter for electronics. Okay, so those are the orbitals we're going to be dealing with, and those are well, I guess we left off S. Okay, we need one more type of bond, don't we? So you can have bonds between S orbital and P orbital. And so sp bond. So now you have, say, an s orbital on atom A, and there's two possibilities. One is a p orbital on atom B. And what's that going to give you? If I draw a line of symmetry through here, what do you notice about the symmetry of those two orbitals? Okay, if I flip the a orbital around this red axis, does anything happen? Does the sign of it change? If I flip the p orbital around that axis, does the sign change? So one's anti-symmetric, one's symmetric. And if I do that integral, what's going to happen? The Coulomb potential is just spherical and always symmetric.
Zero.
It's going to give me 0. Another way to think, I'm integrating over all of space, so the integral for the anything above the red line is going to be positive. Well, ignore the sign of the potential. The integral for everything below the red line will be negative. And then you sum it all up and you get 0. You all happy with that? Nobody looks very happy.
You can just ignore the sign, just don't worry about it. Like, what part is the positive on? Is there like a positive part on the S orbital?
It's all positive. Positive definite. Everywhere positive.
It's all positive on it.
Spherically symmetric. Yeah. So this is positive everywhere. And so this is 0. And it looks like a pi bond between S and P, and there are no pi bonds between S and P. They're 0, and that's why you never even see them mentioned. There's only a sigma bond between S and P, in which you have your S orbital and you have your P orbital, and now you can add it or subtract it. And you know, there's this funny sign change. If I had drawn the p orbital over here and the s orbital over here, plus, minus, plus, then if I add them together, so plus, minus, if I add them, I'll get my symmetric bonding. Subtract them. I don't even know if I can draw it. So if I add them, I get my p orbital, and then I'm going to get sort of an extended region in between, adding them together. And subtracting them, you always kill the stuff in the center. And here, because I got a negative sign in the positive, I'd have to subtract and add. It just depends on which side of the p orbital your s orbital is. But at any point, you still get a bonding, anti-bonding state. And when we talk about, you can look up these matrix elements in tables for the well-known semiconductors, and this would always be referred to as like SP sigma. I don't know why they have to put the sigma, because there is nothing else. If you have an SP bond, it's a sigma bond, because there are no pi bonds. So those are the, what have we got? 1, 2, 3, 4 type of bonds that we have, that we're going to get in these semiconductors we're going to be dealing with. The SS, which is sigma. You have PP sigma, PP pi, and this SP sigma. So if I go back here, this would be PP sigma. It's kind of redundant. This would be SS sigma. There is only one type of bond here. This is PP pi, and we already said for SP there's only one type, which is SP sigma. So those are the type of bonds. That's it. That covers them all for an SP system. And with these, we'll be able to calculate band structure of these common semiconductors and your graphene. And we're going to be drawing more complicated versions of these, but if we start off with a homopolar molecule, which means 2 atoms are the same, and we start off, you'll see these kind of diagrams in textbooks. You start off with a single energy level when they're far apart. This is your energy axis, and it's what we've been doing from the beginning. As you bring these atoms close together, they're going to start feeling each other. They couple, they split, and they split into 2 new energy levels. And we've done this a few times now, where they split by a total of 2T. And this is your anti-bonding, and the lower one's your bonding. And for the, when we do crystals, it'll be your conduction band and your valence band. And for your heteropolar, like gallium arsenide, 2 atoms different, you start off with these two different energies, your cation and your anion, and you with some delta E difference, you bring them together. Again, once they start feeling each other, they're going to couple, split, push apart further, and the two new energy levels. Okay, and so this picture is used, you'll find this in research papers, textbooks, to explain how the individual atomic orbitals evolve as you bring these atoms together to form your crystal. Now let's talk about these p states, in particular what we mean by when I talk about px, py, and pz. If you have a spherical potential, like you have for an atom, then the solution has this form psi of r is equal to some radial. It separates out into the radial part and the angular part. And the radial part's only a function of the magnitude of the how far away you are from the center of the atom, times this angular part, your YLMs, where these are your spherical harmonics. So if you're somewhere out here at position R, this angle off your z-axis is theta, and the other one in plane is phi. So theta is your azimuthal angle, the angle off the z-axis, and phi is the other one in the xy plane. Okay, just so you know which angle is which. And so for your s orbitals, L equals 0, P, L equals 1, and for this course we stop there, and D, L equals 2. We're only going to be dealing with L equals 0 and L equals 1. This full YLM, okay, I'll write it out once. We never use it. But all we need to know is what these things are for L equals 0 and L equals 1, and also the range of M. So M ranges from minus L to L. So M is an element of minus L to ... 0 ... to plus L. And I guess one other thing is that Y L minus M is equal to negative 1 to the M Y L M star. Okay, so with that we have everything we need, but we really only need L equals 0 and L equals 1. And so, for L equal 1, M can be negative 1, 0, or 1, and those are your three p states. So a p state is L equal 1, right? We just wrote that down. S state is trivial. That's just a single radial function. So when L equals 1, M can be negative 1, 0, or 1, and those define your three p states. Let's just write down what these are, all four of them. So we have an S state, which is our Y00, which is just a constant because there's no angular dependence to an S state, only radial dependence. This wave function was separable, so for a S state, you only have a radial dependence. There's no angular dependence at all. Okay, for the p states, as we said, you're going to have three of them. So the first index is L, the second one is M. So this is Y, L equal 1, M equals 0. And so that's square root of 3 over 4 pi cosine theta. That's our Y10. Y11 is equal to negative root 3 over 8 pi sine theta e to the I phi. And Y1, negative 1, is just root 3 over 8 pi sine theta e to the minus I phi. So those are the three p states written in terms as spherical harmonics. We're going to talk about this a lot more when we do spin, but the orbital angular momentum squared L squared is L times L plus 1 h bar squared. These YLMs are eigenstates of the angular momentum operator, but we don't need to worry about that for a while. And the z component of the angular momentum is just, okay, but until we start worrying about spin orbit coupling, we really don't have to worry about the angular momentum operator. And so these are the, what you see when you do the hydrogen atom in, say, your physics, quantum mechanics. But I've been talking about orbitals, p orbitals, px, py, and pz. So, and this is the basis that we're going to be using. Okay, this is the basis that we're actually going to use. So pz, well, that's actually the easiest one. That's just equal to y10, which is this root 3 over 4 pi cosine theta. But remember, theta is that azimuthal angle. So that's just square root 3 over 4 pi times z over r. If you go back and think of that little picture we drew, right? This is r. Here's theta. Z is just r cosine theta, right? Z is r cosine theta. And so cosine theta is z over r. So it has the symmetry of z, and it's pointed in the direction of z, and the sign of this thing will change. As I go across the z-axis, it's positive on the positive. It has the sign of z. So it'll be positive up here and negative down here. And it has the sign of z. And for px and py are going to be linear combinations of those other two orbitals. So px is just equal to y1, negative 1, minus y11, and normalize it over root 2, because these were normalized to begin with. And so if you do that, that's root 3 over 4 pi sine theta cosine phi. Remember, they both had a sine theta. One had an e to the I phi, one had an e to the minus I phi. So one linear combination will give you cosine, another linear combination will give you sine of phi. And that's equal to root 3 over 4 pi sine theta cosine phi. Well, sine theta brings you down to the plane. Cosine phi brings you back to the x-axis, so that's just x over r. So sine theta brings you down to the xy plane. It projects that radial line, it projects this vector down to the xy plane, and then cosine phi projects it back to the x-axis, giving you the x component of r. That's just x over r. So this has the symmetry of x. So again, if you plot this along the x-axis, it's positive for positive x, negative for negative x. It just points along the x-axis. And finally, the other one, py, is just the other linear combination. Well, I guess I have an I involved too. So I over root 2 times y11 plus y1 comma negative 1, which is root 3 over 4 pi sine theta sine phi. And this just projects you over to the y, gives you the y component of that vector. So that's root 3 over 4 pi y over r. So those are the three, these are the ones we're actually going to use, which are oriented along our Cartesian coordinates as our basis for the p orbitals. And once again, I guess that brings us to a close. So there is the homework. We will have a discussion on Friday to discuss the homework.